Hi, this is Dr. John Bergdorf, and in this video, we're going to be looking at systems of equations. In particular, we're going to be looking at systems of two linear equations in two variables. Now, we will see in other videos that solving a system of equations, whatever that means, can be done far more efficiently than by using the method that I'm going to show you in this video. But in this video, we are going to focus on a geometric interpretation of what solving a system means, which is very, very useful to have even as you transfer over to more efficient algebraic methods. So I'm going to share my screen and show you what I'm talking about here. You will see over on the left two equations. This is in fact called a system of equations. There are two equations and two variables. If you will notice, there are no exponents on any of the variables. There are no rational expressions. There's no radical expressions. Both equations are of the form ax plus by equals c, where the a, b, and c are arbitrarily chosen real numbers. Those are called linear equations. And so this is a system of two linear equations in two variables. And we are being asked to solve it. How do we do that? Well, again, we're going to have some more efficient techniques a little bit later, but I want to focus on these equations graphically because, as you may remember from learning other things, the graph of a linear equation in two variables is a straight line. So we should have two straight lines here. I'm going to be using a wonderful and free computer program called Desmos.com, available at the address that you see right here. And I'm going to enter these two equations and see what the corresponding lines look like. So 3x plus 2y equals 12. There's a straight line, but like we were expecting. And 4x minus y equals 5. Another straight line as we were expecting. Notice that these two lines cross each other, which will frequently happen. And they cross at a single point, which Desmos will specifically tell you. All you have to do is hover over that point with your cursor, and it will tell you that that point is 2, 3. Now, simply put, the solution of the system is the ordered pair that corresponds to the point where the graphs cross. So we have solved this system of equations by drawing the graphs and locating that point of intersection. This could have been done by hand. It could have been done on a graphing calculator or by other means. But what we have just done is we have solved the system, and 2, 3 is the solution. Now, even if you move to more algebraic approaches, keep in mind that that system represents two straight lines and they may cross. If two lines cross in a single point, then the solution set of the system of equations contains a single ordered pair, namely the ordered pair that corresponds to the point where the lines cross. And if that happens, we call the system independent. And you might wonder, why do we need a name for the system? The reason for that is when you draw two lines, it turns out that they may not cross. If they do, we call the system independent. If they don't cross in a single point, we'll have to see what that's called. So how could this happen? Let's look at another system here, and I'm going to graph this one. Again, just using Desmos because it's very efficient and very fast. 4x minus 3y equal 12 is 1, and the other is 8x minus 6y equals 20. And notice that these two lines, in fact, do not cross. They are parallel, and that is something that can happen. If the solution if a solution of the system is the point where is the ordered pair corresponding to the point where the lines cross, but the lines never cross, then you don't have a solution. So if two lines are parallel, the solution set of the system of equations is empty. There is no point where they cross, so there's no ordered pair that makes both equations true. And we call that kind of system inconsistent. So if two lines cross in a single point, we call that independent. If two lines are parallel, we call that inconsistent. Now, there's actually a third option, which you might not think of right away. Let's look at these two equations here. 4x plus 10y equals 20, and 6x plus 5y, 15y, sorry, 15y equals, now before I actually enter the last number here, I want to emphasize that this red line represents 4x plus 10y equal 20. Now I'm going to type in 6x plus 15y equal 30. It looks like the red line disappeared. What's really going on is that, guess what? These are actually the exact same line. And that can happen too. Now, if the solution of a system of equations is an ordered pair that corresponds to a point where the lines cross, and the lines are actually the same line, they cross at every point on that line. I'm going to hover over a few here. These are weird looking. There's one that's not quite so weird looking. There's one that's not quite so weird looking. All of these ordered pairs and every other one on that line is a solution of both equations. So there are, in fact, infinitely many solutions. To summarize, if two lines are actually the same line, the solution set of the system of equations consists of infinitely many points, all the points on that common line, and we call that system dependent. So one solution, if the two lines cross in a single point, independent solution, independent system. No solution, parallel lines, inconsistent system. Infinitely many solutions, same line, dependent system. So I hope that that brief description is helpful. Again, we are going to find more efficient algebraic approaches for solving the systems, but recognizing what we are getting geometrically when we solve those systems algebraically will be really, really helpful. So we'll continue on by looking at those algebraic systems, but that's enough for now. Thank you so much.